So thank you all for coming. I appreciate it's quite late, at least here, especially for people further east. And as I guess I'm the last speaker at the conference, I'd like to thank the organizers of this session, FMM, and the general CICM. It's been a great week, and yeah, feel very happy to give this talk. So yeah, this talk is once again about type classes in Lean. I mean, it's a little bit different, and this is a bit more meta, I guess, about a meta program for dealing with type classes rather than a specific structure itself. But it's motivated sort of by the one of the questions really of Adams at the end of Eric's talk, which is what happens in Lean when you keep changing all this stuff all the time and you want to put in some new type class and you've got all this stuff you already did, and you want to know, you know, which of your old stuff maybe still applies to maybe a more general type class that you've suddenly inserted into the hierarchy. So I'll explain a little bit more what I mean in a moment, but you can view these slides on my website. So I will start. So as I said, when you're developing a formal library of you know, a large body of mathematics, it's time consuming to deal with all the small lemmas, right? This has been mentioned a few times already, but the barrier to formalization is quite often not maybe the big outline of the big theorem, but it's really having all the tiny lemmas that you need that aren't quite in the right form or don't quite apply in the context you're working in. And so I want some automated tools that will help us deal with this problem by giving us some extra small lemmas for free, and maybe even some big ones as well. But I'm also interested in sort of, you know, one day in the distant future when all of mathematics is formalized, which, okay, maybe not all of mathematics, but, you know, when maybe there's a nice undergrad curriculum and maybe some people are doing their research math in Lean or in any other system for that matter, in giving some tools that might provide them some insight and might do some of the boring tasks for them. So what am I interested in? Well, it's exactly this problem of type classes. So we use type classes quite often to state assumptions on theorems, things like whether you have a group or a ring structure on some type. And it often happens that you end up with some sort of stronger assumptions than you really need to prove the theorem, right? Because you write something at the start of the file, and then you don't really want to bother thinking halfway down the file, oh, do I need to change my assumption? Do I not need this assumption anymore, but really a slightly different one? And so, yeah, this commonly occurs when we use type classes for algebraic hierarchies or topological order structures or some mixture of these things, you know, topological fields, ordered fields, all of this sort of thing. And I already slipped up and said the word Lean once already. So the examples are in Lean, but really I think what I'm talking about applies more generally, you know, should definitely apply to Coq. And I'd be interested in hearing from any of the Isabel people who are here, what they think of it. And I've already come across some similar in maybe not in method, but in sort of goals work in Misa and also in Coq. So I'll say a little bit about that at the end. But yeah, the examples will be Lean, and hopefully it's readable enough for those of you who aren't Lean experts, and feel free to ask me if it's not. So this is a fake lemma in Lean, just to give an example of what I'm talking about. The reason it's fake is because nobody actually ever did this, but we've assumed that we've got an ordered commutative group, two elements of the group, and we're stating what the inverse of the product is, and we're saying that it's the product of the inverses, but in the same order, right? We've used commutativity. This isn't true in any group, but we've not used the order structure, right? There's no less than sign or less than equal to sign, right? And certainly the proof is, well, one line long. It's just doing a couple of rewrites. It's doing the thing that applies in all groups and then swapping the order. So this is a very silly example, but if it wasn't clear already, I hope it is now. The order structure isn't used, and I want a tool that will tell me automatically, you've done something silly here. You've assumed some extra structure that you didn't use in your statement or its proof. So you can just replace this with com group, and the same proof will work word for word, right? There's no change in the proof needed. And that's kind of one of the keys to what I'm talking about, is that I'm not really trying to do automated proof and generalize things using automated proof. I'm trying to use the existing proof, but just spot cases where the existing proof is sort of using less than the assumptions of the theorem. So that was a rather silly example. Here's one which is hopefully a little bit more interesting. This is a real lemma, which is still in MathLib. So I talked about this a little while ago and no one's fixed it. So I'm quite glad I can still say it's still a thing in MathLib. It's about two fields, and it's about them being positive characteristics. So the characteristic of a field is how many times you add one to itself and end up with zero. So, finite fields, which are a positive characteristic, or infinite fields, which can be characteristic zero, but not all of them are. And we have here a ring homomorphism from one field to the other. And we're saying that in the presence of a ring homomorphism from one field to another, one has characteristic P if and only if the other has characteristic P. And this includes the case of P equals zero being sort of, characteristic zero, which means that there is a copy of Z living inside your field. And so this theorem has a proof in the library. And one thing to note about the proof is that it's sort of entirely symmetric. It's a split and uses a semicolon, which is lean speak for, run the same proof script on both implications. And then it does some kind of, who knows what it's doing, it does some steps. The point is, I don't want to read the proof. I want the linter I'm trying to come up with, the tool, to tell me this automatically so I don't have to read proofs and think about what the assumptions are. And so I think if you ask someone what the correct assumptions for this lemma are, it might actually give people some pause for thought. I don't think it's entirely obvious that, in fact, the first field can be a division ring, which is a sort of like a non-commutative field. And the second field only needs to be a non-trivial semi-ring. So it doesn't need to have inverses, and it doesn't need to be commutative. It's really, almost no assumption at all. You just need some algebraic structure with distributivity. And so this, I think, is a real lemma that's in MathLib, where it would take me a few minutes to work out what the correct type class assumptions are, right? I could go in by hand and start, changing fields to division rings everywhere, but sometimes it's not going to work. So those are two examples to keep in mind. And I'd like to say a little bit more about the first example, because it's kind of the simple case, and how we can, study the proof term and understand which assumptions are used. So this is the sort of instances which are actually used in the proof. So how do type classes work? Well, we make an assumption in square brackets here. And then whenever we apply a lemma, which has some assumptions itself in square brackets, lean fills in the gaps, right? So it fills in sort of the difference between an ordered commutative group and just a commutative semi-group, which is all it needs here. And sorry, I just saw the chat. Get blaming people over here. And we generate these sort of chains of instances with these sort of forgetful maps from one structure to a weaker structure. So we go from an ordered group to an ordered cancellative monoid, from an ordered cancellative monoid to an ordered commutative monoid, from, you get the idea, our commutative group, they should just say to, ordered group to commutative group, and we can visualize it in a sort of a tree-like structure as below. So these are all the instances that appear in the proof of this previous theorem. So this proof here is one line long, it rewrites twice, and it includes all of these, 12 different instances. And this is precisely because the good people in Lean's MathLib have added all these crazy type classes for all these slightly niche algebraic structures because they found them useful. Okay, so here we've got mul1 class, which is something with a multiplication and a 1, but isn't quite a monoid. It doesn't have the same assumptions on the behavior of that mul and 1. Okay, and type classes are used, and this is a really important point, when the structure being inferred is sort of locally unique. You don't want two different group structures on the same type, because that will confuse the type class system. And in the same way, if I've got a com monoid and a group, they both refer to some multiplication, and you don't want to assume that something is a com monoid and a group separately, because then Lean will not know which multiplication you're referring to when you write the multiplication sign. Okay, so if we've got two things which have a common sort of descendant, we have a problem in general. Okay, that's sort of the upshot. So I should say, so this graph here does not include the full sort of type class graph. So there's actually also sort of an arrow in here, but this is just one that doesn't appear in the actual proof of the lemma, right? But there exist more arrows within this graph than in the actual proof term. Okay, so we have to sort of look globally at the graph of all possibilities rather than just looking at the things occurring in the proof term. Okay, so how would such a tool inspect this proof? Well, it would look at all these things which are used. In this case, we're using some assumption about groups and some assumption about commutative monoids, right? In these two rewrites. And so what we do is we look at the group and the commutative monoid, and we find a common ancestor, because we have to take a common ancestor because they sort of conflict, right? They have a common descendant. So we're not allowed to just replace the assumption order to com group by com monoid and group. We have to replace it by com group. That makes sense. So this contrasts slightly to the second example I gave, where the field assumption was replaced by non-trivial and semi-ring, right? So non-trivial and semi-ring do have a common ancestor. The common ancestor is non-empty. So a non-trivial type is one with more than one term. Non-empty type is one with more than 0 terms. So both of these things imply non-empty, but the difference here is that non-empty is a subsingleton. There's sort of a unique non-empty on any given type. And so that's a difference between sort of field generalizing to 2 assumptions in the second example, and order to com group could only generalize to com group in the first example. So what does the global type class graph look like? I just said you have to look at the global graph, right? Well, this is a small segment. This is the stuff which is generated from linear ordered field, which is down here at the bottom. And you can see there's a huge amount going on here. This is just to give you some sense of the scale of the problem. There's something like, I think, 1,000 nodes right now in Mathematicians type class graph. And I'm sure other libraries that use type classes, maybe they haven't gone quite as wild with it, but I'm sure they have a large number as well. And yeah, there's a little link here to a place where you can see how I generated the graph, and you can play with it if you want to take a look. And this was generated in January 2021. I didn't update it. And so it's grown since then. There's some more classes that I showed you on the first slide that actually, if you look closely, aren't in this one. So imagine this, getting bigger and bigger every day. Okay, so it's a big problem. It's not something we can solve maybe by brute force. We have to kind of, think a little bit more about, how do we analyze this graph using some slightly more sophisticated graph theoretic algorithms. Okay. So I want to say a little bit about, why this seemed plausible. First thing I kind of already mentioned, but you're only changing the assumptions to match those things used in the proof. And so ideally the proof script won't need changing. So you're not generating proofs on the fly, you're not doing automated theorem proving, you're just changing assumptions in a way that should hopefully reflect, what's actually there in the proof term. Of course, you could write something by hand, which looks like it was generated by type class inference, and then your proof would need changing, but that's a very rare case that anyone's gonna do something like that. And this should be fast enough to run, right? We want something that we can run kind of interactively, and as we're typing our developments, we can check we didn't do anything silly. And so we don't want to do anything that's sort of too onerous when we're analyzing the graph. So I would say for this purpose, automated theorem proving obviously has come a long way, but this is really not that. This is something different. And so yeah, if we really tried to weaken the assumptions and fix the proofs, that's far more work. So how can we analyze which type class assumptions are the right ones? Well, we can look at the proof term and find the instances that are used for the lemmas that actually occur in the proof term. So, the other things, the dependencies of the proof. And then we look at the global type class graph. And for the things which are actually used, we want to find sort of minimal assumptions that imply those, okay? We can't just use sort of the instances that occur in the proof term, right? Because they might have conflicts, right? They might have sort of common descendants that need to be equal, okay? And so, yeah, we're not allowed to introduce unequal instances of one type class. And so we take meets in this graph, so smallest common ancestors of sets where we group them by sets of sort of conflicting instances. So things where they imply a common descendant, where the descendant is not a subsingleton. So it's something that could have more than one different term of that type. And by doing that, we guarantee that we won't have any conflicts. We won't be confused about which multiplication we're referring to. But also we'll allow sort of the second example I gave, where we did want to generalize one assumption to two assumptions, just where those two assumptions had a sort of a subsingleton common descendant. Okay, so that's roughly the strategy I'm using. I'll say a little bit more about some sort of technical caveats later. And so, yeah, one of the sort of technicalities is that I want to be as general as possible. So I don't want to just look at the type classes which are defined in the library. Okay, so these are the things like group and monoid. We also have sort of things that maybe Eric was talking about, where we have type classes with multiple parameters. So one is a power operation. So a group gives you, you're able to take any element of any group to the power of an integer, and any element of any monoid to the power of a natural number. And so these has-pow things, we have different sort of implications from group to some sort of has-pow, where we've bound one of the parameters to be the integers, and from monoid to has-pow, where we bound one of the parameters to be the natural numbers. So I want to include this information in the graph and include separate nodes for has-pow z and has-pow n, right? So that those things, don't, if I just included has-pow, it would be, unclear which parameter I was talking about. And we treat these sort of partially applied type classes as the basic object of interest. And so this obviously increases the complexity of the tool. Before, where I said we had this graph with 1,000 nodes, well, now I've added even more nodes because I've allowed some of the nodes to be different. Okay. And the second caveat is that it's easy to fool such a tool. I kind of already mentioned this, but if you write a proof where it looks like it uses your assumption, then this won't be caught, right? You really did use the assumption, even though it wasn't necessary. So even simple proofs, especially when automation is involved, the proof script might make use of more than it needs to. And yeah, that's when you get into the realm of more complicated automated theorem proving again. So this is implemented, and the implementation is available on my GitHub. It's not really clean or particularly neat for public consumption, unfortunately, but I'm working on cleaning it up and deleting all the random comments. But it does more or less work. There are some problems with it that I'm still working on, but it functions well enough to be useful, I believe, at this point. So it's implemented using Lean's MATLib, has a so-called linter framework, which are other tools sort of similar to this, where they kind of tell you common errors with your code, maybe things like having repeated assumptions and stuff like that. And that makes it quite convenient just to, have this hashtag lint at the bottom of your file. And as you type a new theorem, a new lemma in, the linter will just check what you're up to and, tell you with a printout when you've done something that it doesn't like. The implementation, it uses sort of native stuff. So, you can't prove anything about the implementation. You might think I'm doing stuff with directed acyclic graphs here. I might want to prove that I really did compute a topological sort. Unfortunately, it's not possible to do that about these specific directed acyclic graphs because they're sort of deep in the lean C++ implementation. Lean 4, I presume, will change this sort of issue quite a lot and make this a non-issue, but in Lean 3, this is a little bit of an issue if you don't trust. Once again, this is a meta program, so if it goes wrong, I don't violate any consistency of the system. It will just be annoying if I made a mistake somewhere. Yeah, we also cache the type class graph and other things like the topological sort and the transitive closure. And that's now made it kind of fast enough for interactive use in many of the files, say in Mathlib. Obviously, some files have these humongous proofs in that confuse things a little bit, but you know, I think, yeah, it's fair enough to use it in many of the files people are working on. And some more kind of details for those who are interested is you want to always inspect the statement as well as the proof. I always talked about the proof term up till now, but sometimes the proof is just riffle, so it's kind of relying on definitional equality, and you don't want to kind of forget one side of your equality. It's really just easiest just to include the statement as well as the proof and get rid of most of those sort of edge cases. Some things maybe look like generalizations, but they sort of mathematically don't really do anything. Things like, you know, if you assume something about the opposite group, you may as well assume it about the group. I just keep a list of kind of things which never really help to generalize and kind of just ban those. And sometimes, you know, the type class mechanism puts in these kind of weird terms which aren't A to reduce. And so, yeah, too detailed. Let's move on. So this is what the output might look like if you run this on something like the file topology algebra group, which discusses topological groups. And it tells you, oh, look, there's all these lemmas in the file about topological groups that really apply to anything with a continuous multiplication. And so this means you're not assuming that the inverse is continuous, right? You're just assuming that the multiplication is continuous. But this is a sort of output you might see, and then you can, you know, if you were working in Lean, you could right-click this and jump to the definition and then go fix it. And this is sort of an iterative process. That's one important point. Once you generalize one lemma, then any lemmas that refer to it might then become generalizable also, right? So currently my answer to that is just to try and make it fast enough that you really can just interactively change one thing, see the next thing that needs changing, change that. But sort of you know, another way of dealing with this would be to try and come up with some system that would sort of transform the declarations in place. So it would run through the whole library and it would change things in memory. And then, you know, when it came to the next lemma, it would look at the changes it had already made. I mean, that would be, yeah, that'd be really great to do, but of course it's far more complicated than the current implementation. So here's maybe some results. So I talked about this a little while ago, and it was really slow. And so now it's fast enough that, you know, I just have a laptop here and it runs overnight on a laptop and will lint the entirety of Mathlib. And so here are just sort of, this is a single pass, right? So maybe there will be more possible generalizations. I think it found, you know, several thousand, but here are some kind of the more common ones that you might find interesting, right? Various things about rings are actually about semi-rings. You know, various things about semi-rings are actually about non-associative semi-rings. So this is one of those examples where someone quite recently decided they wanted non-associative and non-unital rings in Mathlib, despite the fact that ring had been in Mathlib for, you know, 5 years or since the inception of Lean even. So, you know, you've proved for several years many theorems about semi-rings, and then suddenly someone weakens one of the assumptions. And so this is a classic example of where you don't want to go by hand trying to generalize everything. You really want a tool to tell you, oh, these lemmas that you proved 2 years ago apply in the more general setting. So it's quite good to see this sort of thing showing up. Some other ones that I think are quite funny, I mean, several here that I've denoted with these round brackets is where you've weakened one assumption to a group of 3 assumptions. So this is a COM semi-ring, and it's going to, okay, well, it's hard to say what it's going to because I didn't write the operations in here, but we'll leave that example. One other one I just want to point out was in the integral domain, some of them are generalized to COM ring with no zero divisors, which to a mathematician maybe sounds like exactly the same thing. But in fact, the difference between these two is that the integral domain assumes that it's non-trivial, whereas this doesn't. And the reason that I think is kind of nice is because, you know, these sort of non-trivial assumptions are just this sort of annoying things that you are proving something, and then suddenly you have to prove that the thing you're talking about is non-trivial. And, you know, that's just, not something you're thinking about when you're thinking about mathematics, is my ring trivial or not? And so it's nice to remove those assumptions where possible, even though it doesn't give you a stronger theorem, really. Okay, I'll just maybe wrap up in the last couple of minutes by talking about some other systems. So type classes are used in a similar way in other systems. I'm not really an expert on all the different systems out there, so I'm sure I'm missing some that use type classes. But two things that I've come across quite recently that are related in kind of the spirit of what they're trying to do, but different. So there's a Mizar paper by Jesse Alamar, which is about reducing assumptions on binary operators. And so it's kind of a bit more brute force, and that kind of comes into the reason for that maybe is that Mizar is so much faster than Lean for what it does, that you can really just change these things on the fly and just see what breaks. Whereas in Lean, that would take far too long to sort of rebuild the whole library every time you made one change. This is a Koch paper that, by Olivier Pons that also kind of aims to generalize theorems, but it doesn't really talk about type classes specifically, but similar in spirit in that they want to generalize assumptions based on relaxing assumptions. Relaxing assumptions on types. So maybe some future work would be, well, here's a list of things. I think I'll wrap up there and leave some time for questions. So thank you very much, everyone.
Thank you for this great presentation. And so let's go to questions. I saw in chat that, okay, Marasmia first.
Yeah, so I guess you were talking about with the integral domain, maybe if you change you generalize it, then you don't need this assumption of non-triviality. Now, is in some lemma that assumption was included not as an instance, but as just a hypothesis? That would then change the. I mean, you could then possibly remove that hypothesis. So then you'd have a different theorem. I guess what I'm talking about is, as well as doing this for type classes, you could do it for hypotheses as well, but then you'd have different results.
Yeah. You're right that sort of in principle, there's nothing too specific about type classes. Just what's nice about type classes is, you don't change the proof script because it's an automatic system. If you want to generalize other assumptions, you really have to start making modifications to the signatures of things in the way that they're typed in Lean. And it definitely does apply more generally. It's just, I think type classes are also really a natural source of this sort of problem. I think when people are typing the assumptions by hand, maybe they think a little bit more about what they're using. And so I would have to experiment to get a better answer about how common that is. But definitely, in principle, you could think about non-type class assumption as well.
Okay.
Yes, exactly. As Mario says, as soon as you use this tool, then maybe the one that catches unused hypothesis will also kick in, and they kind of feed off each other or something.
And Konstantin?
Hi, thank you for the talk. I would imagine there could be several generalizations that are incompatible. Like, for example, if you have several structures, you will relax condition one, but that forces you to fix the conditions on the other, or vice versa. Yes. So how you deal with different generalizations?
Yeah, I haven't dealt with that. So currently, I've implemented this thing to find a meet, and it's based on a topological sort, and that's kind of arbitrary. So I think at the moment it will sort of break ties completely arbitrarily. And you're right, it would be good to, have an extension that would, find all possibilities. I'm not quite sure how common it is to have that sort of structure showing up in this sort of mathematical hierarchy, like the one in MATLAB, but you're right, in principle, it could happen, yeah.
Okay, thank you.
There's a question from Kevin.
Hi, very nice talk, Alex. You claimed when you showed us that picture of 1,000 type classes
Oh, that wasn't the 4000. That was
Yeah. But you claimed that these type classes had been introduced because we'd found them useful. And I'm not entirely sure that that's true for these random things like commutative semigroups. I just think that people like Mario and Johannes just put them in because that was just the way they were thinking about mathematics. And do you have any evidence that these funny things at the bottom of the type class hierarchy that mathematicians never use, but are there anyway, like commutative semigroups, are they just getting in your way?
I mean, commutative well, I defer the question to maybe to Eric or someone. Yeah, I don't know. I personally believe that these things are useful, and there's all sorts of like weird structures that come up the other day that you've never heard of. Like I was doing some number theory the other day, Kevin, and I had to learn what a near ring was. I mean, it's these things happen sometimes. Maybe they're less common than rings, but I don't know. I'm inclined to believe that all mathematics is useful. But.
Okay, and you're demonstrating that, in fact, however many silly little type classes we throw at you, your tool can still hack through them.
Hopefully, yeah.
This tool will make them look useful, right? Because suddenly tons of lemons will use these tiny type classes.
Exactly.
Yeah, we see the power of non-associative semi-rings, because now there's how many lemmas did you say? How many lemmas about rings should actually be about?
This is a lower bound, but
55 lemmas about rings should be about semi. You see, and there's me poo-pooing semi-rings. It's like,
well, I mean, yeah. I think Mario had a question in the chat. Am I preparing a massive PR? No, I was thinking about maybe kind of starting at the bottom. The roots, the leaves, whichever way you want to look at it, of the import hierarchy. And maybe trying to work up file by file, but yeah, it's a big job, I think, and I'm not really quite sure how best to approach it still.
All right, and I just think that those changes, if you apply them to the library, may propagate. You said that you should also iterate this process, so
yeah, exactly.
Those numbers can go up.
Yeah, that's why I wanted to start with the leaves, because if you start with the file maybe that you care about most, and then you fix it, and then you fix a file that it imports, and then you have to go back and fix the one you did before. So I think if you were to do this at scale and really try and stop this tool complaining, you would want to start at the top of the import hierarchy to save yourself effort switching files all the time. Yeah.